Hello, my name's Brian Handy. I'm a consultant in physical chemistry working in the nuclear power industry. The first part of the presentation was pressurized water reactors normal operation. In this part, part two, I'm going to concentrate on accident chemistry. Accident chemistry mainly concerned with design basis faults. In other words, loss of coolant accidents, steam generator tube rupture, auxiliary building faults and field handling accidents. But there's also severe accidents. This topic is a vast area in itself, and I really don't have time to present all the material in this presentation. So when considering faults, we look at the event sequence. In other words, the water masses in the system, the flow rates, temperature and pressure. We consider the water chemistry, that's the pH, in other words, the boric acid, lithium hydroxide, and the redox conditions with the oxygen concentrations. In a fault situation in the primary circuit, safety injections introduced which contains oxygen. We need to consider fission products as well, what the initial conditions are, what the concentrations are, and what the speciation is. And for the fission products, cesium is an important fission product. It's volatile. It exists as the CS plus ion, and generally speaking follows water and droplets. In other words, the thermal hydraulics of the system. The noble gases like krypton and xenon will enter the gas phase, very little retention in the water phase. But iodine chemistry is rather more complex because some species are volatile, and these can transfer into the gas phase via mass transfer. We'll also need to consider corrosion products and actinides. As I mentioned before, these can deposit on surfaces, and during a transient or a fault situation, it's possible that a fraction of these get released into the primary coolant. So coming back to iodine, this can exist in many oxidation states ranging from -1 to +7. And the examples of these species are shown here, some of which are stable, like I-, I2, HOI, its hydrolysis product. Then there's iodate, oxidation state +5, and periodate, oxidation state +7. The other species are free radicals, so they're in very low concentration, so they don't contribute to the volatility as such. Some of the stable species are volatile, of course, like I2 and HOI. We'll also have to consider organic iodine. Now, if iodine is released into containment, it can interact with organic matter, mainly painted surfaces, and produce organic iodine, such as methyl iodide, which is again a volatile species and can enter the gas phase. So in recent safety case analysis, we adopt a kinetic approach, and this considers radiolytic reactions, and we have a high dose and low dose model to describe this. Before we go on to radiolytic reactions, I just want to say a few words about the thermal reactions. Thermal reactions aren't quite as important, but nevertheless we still have to consider them. And I'm not going to dwell on the numbers here because these are just the equilibrium constants for the reactions taken from the literature. I'll just point out one or two of the important ones, and I'll say the second one down is the hydrolysis of I2. The first one, the I3- formation, is only important at high concentrations. And then there's the dissociation of the various acids like HI, HOI, of course, and oxidation. That's the fifth one down, which is the reverse oxidation, the way it's written there, of I-. And the volatility of the iodine species is determined by what's called a partition coefficient. This is the ratio of concentration in the aqueous phase to that in the gas phase by volume, of course, is PV. And we've got the main species here, like HI, which is important in steam tube rupture faults, I2 and its hydrolysis product, HOI, important in loss of coolant accidents. So coming back to radiolytic reactions now, I mentioned that in the water radiolysis system, there's about 30 reactions, and in the iodine system, there's similarly another about 30 reactions with iodine species. But all this can be simplified because the production of oxidizing species from water has a G value of 2.8, and production of the reducing species has a G value of 2.7. And the sort of reactions that lead to the oxidation of iodine, for example, the OH radical oxidizing I- minus to iodine atoms which can recombine to I2, and also conversely, reactions that lead to reduction of iodine are via O2 minus, and that can react with I2 to form I minus, and indeed it reacts with the OH radical, O2 minus and OH, to form oxygen and hydroxide ions. So the net result is the oxidation of iodine, iodide I should say, with a G value of 0.1, that's 2.8 minus 2.7 for iodine atom production, or we could say it's a G value of 0.05 for I2 production. And this is continuous, for a low dose process, continuous for doses up to 5 kilogray. Now, for the low dose model, we could say that the rate of production of species is some constant times the dose rate times the G value. And this constant's really a conversion factor. What we're really interested in is the rate of species in moles per litre per second, because that's a meaningful quantity to the chemist. And if the dose rate's in grays per hour and the G values in molecules per 100 EV, we need to convert a conversion factor K, which takes into account of all these factors. For example, converting grays to electron volts and hours to seconds and so on. And we end up with a K value of 2.88 times 10 to the minus 11. Now, in the high dose model, I mentioned that up to 5 kilogray, we reach a radiolytic steady state. In other words, the rate of oxidation of iodine equals the rate of reduction of iodine. Now, this is just a schematic. In reality, it's a curve, but for safety case purposes, we assume an initial slope there going from 0 up to 5 kilogray at a G value of 0.1. And in the steady state condition, we find that the fraction of iodine oxidized is very much temperature dependent. You can see from this curve here, at high temperatures, we've got a fairly low degree of oxidation of iodine. This is about 7 times 10 to the minus 4. Whereas as you're approaching ambient temperature, low temperature, we can have as much as 25% of the iodine oxidized in the steady state. But it's the mass transfer which determines the relative release of volatile species into the gas phase. And mass transfer rate is really a mass transfer coefficient multiplied by an interfacial surface area multiplied by a concentration difference. So the units of Km are in velocity units, meters per second, and we can write dm by dt equals Ka C1 minus C2, where C1 and C2 are the difference in concentrations there from one region to another. But in the diagram at the bottom right there, we're going from liquid phase to gas phase, and our C2 is in fact a virtual concentration of the liquid phase. So if we've got C2 G as the gas phase, its virtual concentration and equilibrium will be PV times Cg, and so the driving force is the difference between the actual concentration in the liquid phase minus PV Cg. So our equation then becomes the one at the bottom there, dm by dt equals Ka in bracket Cl minus PV Cg. Now the mass transfer coefficient is calculated from the aqueous phase or liquid side mass transfer coefficient and the gas side, and these are derived from simple boundary layer theory, but the result is different if you're going from aqueous phase to gas phase. Or from gas phase to aqueous phase. You can see that the equations there are slightly different, and they just differ by a factor of PV, in fact. But to calculate Cl and Cg, we can use standard chemical engineering correlations to calculate the mass transfer coefficients. So these correlations are found in the literature, and they can be applied to transfer from ventilated deep pools, from thin films, transfer from aerosol droplets into containment, or from gas phase to spray droplets. And here's a typical example. This is transfer from a pool to a containment atmosphere. And we could see that the gas side mass transfer coefficient is dependent on the Reynolds number. And it's a different correlation depending on whether you've got a high or a low Reynolds number. It also depends on the diffusion coefficient, the density and the viscosity. And the water side mass transfer coefficient depends on the gas velocity and the Schmidt number. And as an example here, if you, these are just equations relating the change in iodine species. The first one there just represents the depletion of I- in the aerosol from radiolytic oxidation. The second equation, you've got the build-up of HOI and I2 in the aerosol, and that's dependent on the radiolytic oxidation rate there, the first term. Then you've got two mass transfer terms there, one for HOI and one for I2, both representing the release into the gas phase. And the concentrations of HOI and I2 are related by the I2 hydrolysis equilibrium constant, the third equation there. And the gas phase, similarly, for the two species, you've got two terms there for the mass transfer for HOI and I2. In the sump, the first one really, mass balance equations, the fraction of iodine is equal to the sum of the two species there, the two volatile species. And similarly, the I minus in the sump will be 1 minus F times the total iodine species. And then you've got the total iodine is the sum of the concentrations of the three species present. Then the rate of disappearance of iodine from the sump is just given by the two mass transfer terms. And again, the two concentrations of the species are related by the equilibrium constant. Now, I apologise for the postage stamp diagrams there, but it just gives you a feel for the concentration profiles. So the first one is just the I minus concentration decreasing. The second one is the HOI increasing, and the I2 increases initially and then starts decreasing again. This is in the aerosol. There's the radiolytic buildup and then the release into the gas phase. And similarly at the bottom there, you've got the HOI and the I2 in the gas phase. So to summarise, chemistry is applied to many areas within the liquor industry. The current two presentations are focused on pressurized water reactors. Normal operation of the PWR was discussed in the previous presentation, but this presentation concentrates on PWR accident chemistry, in other words, the chemistry of fission products, where in particular iodine is more important and more complex than the fission product chemistry. And you'll have noticed in the presentation that there's an interaction of chemistry, physics, in other words, the thermal hydraulics of the system, the engineering, how the plant works, and the mathematical treatment of the fission products. So advice to early careers. The chemistry within the nuclear power industry is multidisciplinary. We need to embrace the following areas: the physics, in other words, the basic nuclear physics, engineering and how the plant operates, chemical engineering aspects, for example, mass transfer, the associated mathematics, and this could involve solving coupled differential equations. The development of presentation skills, i.e. written report production and all presentations, is also important. Well, I'm going to stop there. I'd like to thank you all for listening, and I hope you found it interesting.